think we're ready to get started. Today we'll have Mr. Yuanjie speaking to us from Professor Tutungler's group. He's been here from Tongji and then Southeast University, where he got bachelor's and master's respectively. He's in the later stages of his PhD. Yeah, so he'll be finishing relatively soon. Today he's talking about a topic that he won a Best Paper Award at TRB this year, so this should be exciting to hear about. And it's on gradation effects influencing mechanical properties of base and sub-base materials in Minnesota particularly, but I think we can learn something for Illinois or anywhere else, right? Yeah, so. Okay, let's welcome Yuanjie.
Thank you, everyone. Today my talk is about gradation effects influencing mechanical properties of aggregate base granular sub-base material in Minnesota. So as defined by the title, so we studied the Minnesota granular base and sub-base materials specifically. Before I move on, I'd like to acknowledge other contributors, Professor Tutungler, Mr. Yu Chen, and Mr. John Sigma from Minnesota Department of Transportation. And this presentation will be mainly about the experimental investigation. At the end, I will try to briefly mention the numerical simulation work we are pursuing right now. The keyboard doesn't work. How can I, do I have a control? It doesn't work.
What page down? Here, let's. Seems like it's locked up.
Okay. So in my presentation, I will first talk about introduction and motivation, and then I will talk about some literature related to this topic, and then describe the mean dot aggregate base we collected with some analysis of experimental results, and then I will conclude with some implications. So according to NCHRP 4-23 study, pavement distresses can be related to base quality, especially like stiffness and strength. And this summarizes some critical aggregate properties related to pavement performance. As you can see, like shear strength, stiffness are among those aggregate properties. And you can see that gradation is almost related to all of the aggregate properties. So that's why we need to have a better understanding of gradation mechanism. Recently, there's a NCHRP synthesis completed by Professor Tutungler and Deb. As you can see, like 95% of the responding agencies, they construct unbound aggregate layers for base course. All the responding agencies construct unbound aggregate layers for flexor pavements. It's interesting to note that about 70% of the responding agencies construct unbound aggregates for rigid pavements. And 94% of the responding agencies use unbound aggregate layers for dense graded coarse layer. So as you can see, like unbound aggregate layers has a lot of applications in the pavement area. And based on this, the motivation of this study, because by realizing that gradation is a key factor influencing resilient modulus, shear strength, and permanent deformation of unbound aggregates, so we need to have in-depth and a better understanding about the mechanism. Current gradation specifications used by many transportation DOTs, they just specify gradation binds, and there are some improvements we can make to further improve those specifications. For example, there's no robust linkage between actual performance. We know that those gradation binds works well for some standard materials, but they will not guarantee good performance as always. And then sometimes we may have conflicting performance requirements. For example, to ensure stability, we may compromise the drainability or permeability sometimes. And the other thing is like within that gradation binds, then how to distinguish between different gradations within that bind is still an issue. Recently, many state DOTs are facing problems like using out of specification materials. So we need to come up with a justification to accept or reject those materials properly. Typically, unbound aggregates can be classified for different uses based on their physical properties, including mineralogy, type of rocks, and then other features like high plastic fines, particle strength, gradation, durability, shape, as well as deleterious materials content, so on and so forth. As you can see, I mean, those properties are very empirical in nature and may not have a strong indication of the mechanistic performance. So that's why we need to pursue mechanistic classification. Here is an example I would like to show. On the left-hand side, you can see like 4 different types of rocks: hard limestone, soft limestone, clastic gravel, eruptive rocks. If we evaluate those materials just based on the Los Angeles aberration values, then we can see like soft rocks, as indicated, they may not be good because they have very high LA aberration values. However, if you look at the figure on the right-hand side, if we examine it from the permanent strain as well as the resilient modulus, then we can say like it's kind of a preferred material because it has lower permanent strain but higher resilient modulus. So this confirms that physical classification may not have a robust linkage between actual performance. Although mechanistic classification is good, but in reality, not every transportation agency have the capability to run experimental tests. According to this NCHB synthesis, out of 50 states in the US, only like 10 or 6 run laboratory testing for unbound materials. So that's why we need to focus on the mechanistic side, but still try to be practical as possible. So based on this, the objective of this study is to explore from a well-established mean dot aggregate database the robust linkage between quantitative gradation parameters and the critical mechanical behavior of aggregate materials. And the next objective is establish such linkage and then validate such linkage so that we can use this as a guideline to utilize limited aggregate source with optimal properties to design pavement layers for site-specific design traffic level and environmental conditions. Another goal is to further develop performance-based material specification. Mainly, for example, at this stage, we are focusing mainly on the gradation and the shape properties. Try to improve the current state mean dot specifications. So regarding the literature review, as you may know, like these are the several typical gradation types: well graded, gap graded, open graded. So for pavement, unbound pavement layers in flexible pavements, we typically use like well graded, dense graded materials. They have grain-to-grain contact, low air voids, and high density. Through the literature review, we can find a lot of gradation quantification methods. So here is just a sample of those. It's hard to be exhaustive. So the most familiar one may be the Tarbell equation, the maximum density line. Most of you are familiar with this. And then the second one is suitable for like materials generated by crushing, mining, and grinding. And the USCS specification unified soil classification system also classify different size of materials into gravel and sand based on their definitions. And then we have the Bailey method, which is quite well practiced in asphalt mixture. Still, we need to try to explore the application of this method for unbound aggregates. For concrete mixture design, there are like this method distribution basically is just a plot of individual person returned versus the sieve size. It's used quite frequently for concrete mix design. And another method for concrete mix design is closeness factor. They use like, based on gradation, you calculate closeness factor and the workability factors, and then come up with different zones for different properties. In addition to those gradation quantification methods, there are a lot of packing models to describe the aggregate packing. For example, in geotechnical engineering, for cohesionless soil gravel mixture, there are a lot of triaxial shear strength test results. This table shows the shear strength as a function of percent gravel by weight in the gravel sand mixture. As you can see from this table, so when aggregate gravel fraction is greater than 70% by weight, then the shear strength is mainly controlled by the gravel. If the gravel fraction is less than 49%, then the shear strength is mainly controlled by the sand fraction. So as you can see, like the shear strength depends on the relative concentration of the large and the small fractions. So the important thing to catch is the porosity developed in the mixture and type of structure support are the critical factors for shear strength. A recent paper described the packing theory for unbound aggregates. So you can see they calculate the aggregate packing into primary and secondary structures. Based on those definitions, they came up with several important parameters, like void ratio in the secondary structure, void ratio in the primary structure, as well as the disruptive potential. So, and they could find that the disruption potential is well correlated to the CBR values. And I mean, the previous examples are mainly on the experimental side. There are a lot of numerical simulations to investigate the gradation effects. Discrete element is a well-used tool because unbound aggregates are particulated in nature. So in this study, you can see they performed some 3D numerical triaxial compression tests to study the effects of grading on stress-strain behavior and dilatancy behavior. As you can see from this figure, there are some significant difference in terms of the gradation change. And this just gives you some example, and I'm not going to the details of those study. Another thing is that we can use micromechanics-based methods to quantify the material spatial heterogeneity. As shown in this example, they can map material property variation into the finite element mesh, and based on the spatial distribution of particle size and the shape indices, then they come up with a micromechanical-based framework to quantify the influence of those variables. Giving some information about this project and as well as some literature. So now I would like to move on to the database we collected. Here, before describing the database, I would like to give some introduction about the mean dot specifications. As you can see, this shows the gradation binds for different classes specified by mean dot. For your reference, i.cs6 is also included. And this table summarizes different aggregate classes as well as the typical resilient modulus assigned to each class during different seasons for analysis in mean pay program. So basically, aggregate base, including class 5, 6, 7. Class 5 requires at least 10% crushed. Class 6 requires at least 15% crushed. Class 7 is basically for recycled materials. For granular subbase, mainly like class 3, class 4, synthetic granular. So the database we collected, including both the resilient modulus and the shear strength. So they tested virgin materials as well as recycled materials. Those materials were collected from different construction project sites, or from generated for specific research studies at the University of Minnesota. So basically, it's a variety of materials. And some of the materials are tested in mean dot central lab. Some of them are tested in the U of M lab. So, but eventually it's compiled a huge database. So we were able to collect this database and use for our purpose. It's good to emphasize that the resilient modulus test they have done follows the NCHRB 1-28 procedure. They also have the shear strength test results. Basically, at the end of the resilient modulus, they failed the sample to collect the peak deviated stress as a failure. And this table just summarizes the information about the materials we collected for the shear strength analysis. As you can see, there are two categories: standard materials, non-standard materials, different class, and different confining pressure for the peak deviated stress at the failure. So because it involves different types of gradations, so we were able to have the opportunity to analyze the gradation effects. This just shows the gradation of those materials. As you can see, for each type, some of the gradation may be out of the bind, so maybe considered as out of specification. And you can see some variation in the gradation for those different materials. So after that, I want to go to the analysis results. It's need to emphasize that because those materials are tested at different labs, collected from different project sites, so there may be some variation inside, and in order to try to minimize the variations, we eliminate some data sets. For example, we stick to the data sets which have optimum moisture content fluctuation around 0.5%, and the relative compaction level is within 99 to 101%. So some data sets are not following this requirement. We didn't use, just to make sure that the samples we started are approximately at the optimum condition. As well, in order to minimize aggregate mineralogy and shape effects, so we group each sample according to their aggregate types. And this is just the typical results showing the modulus shear strength relationship. So according to the mechanistic classification, resilient modulus and shear strength is indicators for the mechanical performance. So this figure shows, like, for example, 4 types: gravel, limestone, granite, gravel, at different confining pressures. If we use the mean dot criteria for resilient modulus and peak deviated stress at failure at a specific confining pressure level, we can see like 2 different zones: beta quality and lower quality. The important thing to catch here is that for limestone, in the lower quality area, for gravel, sometimes we think that they may be bad materials. But as you can see from the right-hand side, it actually fall into the zones of bad quality. So the information to catch here is that the modulus strength relationship is not unique for aggregates. So the better indicate for their performance is, I think, is a shear strength indicate, as Professor Thompson emphasized before, that lotting behavior is a primary indicator of unbound aggregates. So modulus, if we just look at the modulus, sometimes can be misleading. Once we have all the gradation, then we categorize the gradation based on the previous methods to calculate the quantitative gradation parameters, and then we try to correlate those gradation parameters to shear strength. After some statistical analysis, we found out that this parameter, gravel to sand ratio, calculate using this formula, so it has a much better correlation with shear strength properties. This shows some results regarding this, how this parameter affecting the strength. After some data analysis, based on our data analysis and the previous literature, we came up with that there is an optimum range for this value to achieve the maximum shear strength. So instead of going to the details here, I just quickly summarize some results. So after some data analysis, we found that this range for mean dot materials, the range is typically around 1.5 to 1.7. As you can see in the above figure, for GS ratio around 1.5, the peak deviated stress at failure is kind of maximum. And the bottom figure shows that as the GS ratio approaching 1.5, peak deviated stress increases. So the trend is kind of obvious for the bottom figure, but for the upper figure, there's some kind of not that obvious, because it involves some recycled materials. So according to a report completed for mean dot, specimens with increased lab content exhibited higher permanent deformation. So as you can see, like 50% lab, 100% lab here shows pretty much the same peak deviated stress at the failure. But actually, according to Kim and the Labus study, so there should be some difference in their shear strength behavior. So we were guessing that the similar peak deviated stress failure may be due to the GS ratio, because if you reach the optimum GS ratio, then the shear strength behavior kind of can be improved. This is an assumption we made, and then we try to confirm this assumption from our own database and external databases. Here's just before I move on to the validation stage, I just want to give a quick interpolation about this parameter. So basically, we consider the mixture as a grain size, gravel size, and the sand size based on the USCS specification. So gravel size means passing 75 millimeter returned on number 4 sieve size. Sand size means passing number 4 and returned between 75 micrometer. As you can see, if we have a large GS ratio, that means gravel size dominate in the mixture, then the sand size just fills voids between those gravel size particles. So there should be some optimum range for each specific gradation. And then we try to interpolate the results from the porosity and the point of view. As you can see, like the first figure, plus the maximum dry density versus GS ratio, optimum moisture content versus GS ratio. Since we don't have the specific gravity information about those materials, so we couldn't interpolate the results directly from porosity. So here is just kind of approximation about the porosity. As you can see, like GS ratio within the range around 1.5, then we can have the maximum dry density, and the optimum moisture content is kind of the lowest. So based on this database analysis, after some statistical analysis, we came up with this range about 1.5. Then we try to use some other databases, try to validate this range. So the first database we selected is from Professor Thompson's early study in 1997. Actually, this database was specifically for mean load materials. So those materials were collected from mean load and sent to HO to test for large rapid shear. So as you can see from these results, so because we just studied the samples at the optimum condition, so we eliminate those samples were not at the optimum, because some of the samples were studied for moisture effects, so moisture level is and density level is not around optimum, we didn't use. And as you can see kind of from the left figure, as GS ratio increases, there's kind of increasing trend in the optimum moisture content, and well as a decreasing trend for the maximum dry density. The right figure shows the permanent strain, which is kind of an indicator for shear strength, and as well as resilient modulus versus GS ratio. So this is first thing to catch that the resilient modulus has no clear trends with permanent strain. That means those two things probably are not directly correlated, because when we talk about resilient modulus, then we are talking about the elastic range. When we talk about the permanent strain, there's kind of stress level beyond elastic stage. So sometimes it might be confusing to correlate those two things together. So in permanent design, when we specifically focus on the resilient modulus, sometimes can cause some catastrophic failure.
Can you explain, you said there was no trend between resilient modulus and permanent strain?
As you can see, like the permanent strain decreases with the GS ratio, but at the same time, the resilient modulus is kind of increasing with GS ratio. So
there's a relationship between permanent strain and resilient modulus, but not with GS ratio in between. Is that right?
Can you repeat?
Yeah,
You said the permanent strain and resilient strain aren't related, but it seems like they are related in that case. I assume you're testing the same aggregate, one in permanent strain. If it has higher permanent strain, it has lower resilient modulus, irrespective of the G sub S.
Yeah, basically what professor is saying that is that one is decreasing, one is increasing. So that would probably mean that they are kind of, there is a relationship.
Oh, okay. So maybe
I know they're not related through, you can't, I think what you maybe meant to say was G of S doesn't, higher G sub S doesn't necessarily tell you, actually it does tell you the right property. So I wasn't sure what your point was.
Oh yes, I think that's the point I was going to make. Maybe I didn't make it clear. So the point to make here is that since we found optimum range from our previous database, so it's like a 1.5. So basically 1.5 to 1.7 is the optimum range. So basically when you increasing to 1.5, there's kind of like shear strength peak deviated sigma d is kind of increasing. And then it reach a kind of a maximum level. And then when you increase further beyond 1.7, then it starts to decreasing. So
Isn't shown in this figure.
yes, this figure, it shows like just down to, because the maximum GS ratio we can calculate is just between 0.8 to 1. So we were just to confirm the trends between from 0 to 1.5, this range. And
one quick question: is the y-axis correct? Permanent strain, is that as high as 20%? Looks like there may be a decimal missing somewhere. Probably 2%. There may be an extra 0 there. You can check it later.
okay.
Go ahead.
When I talk about the relationship between permanent strain and resilient modulus, so I was trying to say that higher resilient modulus doesn't necessarily always give you the lower permanent strain. So I think that's the point I was trying to make.
Yeah, and that may be true, but that's not true from this graph,
Right?
Yeah, there's a figure, so
Okay, sorry.
I think I made that point based on that figure, and then we connected one database from University of Oklahoma. I think that was complete in 1998. They studied sandstone and limestone, two different types, different gradations they used. So we kind of also use this database. The optimum range we found from, for example, from left figure, there's optimum moisture content and dry density versus GS ratio. Kind of like the optimum range is about 2. The value is higher because for mean dot they used Ashito T99 standard compaction. For this one they used Ashito T180, so modified compaction. So because of the compaction level is higher, so maybe the range is kind of higher. And the right side plus the uncompressive compressive strength versus GL ratio as well as the resilient modulus. As you can see, like so the solid symbols represent the shear strength. The hollow symbols represent the resilient modulus. So as you can see, so around GS ratio of 2, the compressive strength is kind of reach its maximum. That's the main thing we want to catch here, because we focus specifically on the shear strength side. Sometimes resilient modulus and the shear strength doesn't have the unique relationship. So as you can see, like as resilient modulus increases, sometimes the for this figure, resilient modulus increases, but the compressive strength doesn't necessarily increase. Another database we used was from depth study. So that one was not specifically for gradation effect. So the gradation was well controlled, and only the percent finds was changed. So we also calculate GS ratio for this one. And on the left-hand side, as you can see, the GS ratio, optimum moisture content, and maximum density relationship. The range we identified was for different types of rocks was kind of a little bit different. So the range we found, the optimum value we found was 1.6, 1.68, something like that, because there are some variations in the specific gravity. So the important thing to catch here is a right-hand side figure. So as you can see, at GS ratio around 1.6, the peak deviated stress at failure for those three types of aggregates are more or less at its maximum. So the previous slide shows we established this kind of the optimal range for this parameter, and then we try to validate this parameter, this range, using some 3 external databases. Here's an application of this gradation optimization method. So here shows an example of class 5 gradation binds. Based on the upper bound and the lower bound of this gradation, we can calculate the GS value for this gradation bind. So basically, each point here represents a gradation curve, because we can fit this curve using Tilbert's equation and calculate GS ratio based on the formula we came up with. So these contours represent different GS ratio values. So based on our study, 1.5 to 1.7 is kind of optimal range for the shear strength behavior. So for once we have a gradation, then we can try to calculate this value and give us a quick idea about how much shear strength, how better the shear strength behavior for this specific gradation. Then once we validate this method, then we don't need to run lab testing for each gradation every time. So that's the main logic behind this method. Then I will talk about the conclusions. So based on the previous figure, you can see that the modulus strength doesn't always have the unique increasing or decreasing trends. So we found that it may be inadequate to establish aggregate quality based just on the resilient modulus. Especially in the MEPDG guide, they just focusing. Recently they focus on the resilient modulus side, but regarding of the rotting behavior and the shear strength, I think we need to have more inputs to quantify those behaviors. And to avoid rotting failure, so we came up with a limiting shear stress ratio and suggest for their use in the future. Gradation effects on the shear stress behavior was quantified from this GS ratio, and the optimal range found for mean dot aggregates was around 1.5, based on the acetyl T99 standard compaction. And this value was kind of verified using 3 external databases. Here shows some application of this method. Mean node test section 13 is kind of under reconstruction. So they request unbound aggregate base for this recycled PCC pavement. So this pavement structure is like 7.5 PCC and 7.5 inch 100% recycled. So for this materials, it's required to have better shear strength behavior and locking behavior, as well as to maintain the durability. So using this framework, we came up with a gradation and sent back to them, and they hopefully we can get some instrumentation data and feedback from the real construction. Then we can further validate and redefine this framework. Another thing we are working on now is try to, because we identified this parameter mainly from experimental investigation, see we are still in the stage to further validate this framework. So we pursue to utilize the discrete element method. So since we already have a well-established database in 2008, completed by Professor Tutumra and his student. So this study investigates 6 different types of aggregates, just one gradation, different shape effects. So we are hoping that we can calibrate the DM model parameters using this database. Once the DM model are calibrated, then we can use it to study the different combinations of shape and gradation to further redefine the current mean dollar specifications. With that, I would like to thank you for your attention and welcome any questions.
Any questions for Yuanjie? No questions? I got a question. Why? I'm trying to figure out. You usually get aggregates because they come as they are. So I'm kind of trying to figure out how you're going to actually change the gradation.
Are you talking about this part?
Well, you're saying the gravel sand ratio is this indicator, but in the end, not all the aggregates come with those correct gradation. Those by aggregates. How do you deal with that? You're grading these for yourself, or this is how the aggregates come? You understand my question?
So you're asking if I have materials with some gradation, then.
Well, I'm just saying that are your calculations based on an aggregate that's delivered like that, or it's something that you've made within a band to improve the properties?
I think those database, the aggregates involved in those databases, they came from real construction projects.
Okay.
So, for example, there's a highway construction project. They just send out some stuff to get the materials. So I think those gradations are are not artificially made. So they are generated for specific either construction projects or research studies.
All right, I got you.
I guess he's proposing just to modify the state specs. So, for example, CSX, whatever the limits are. If he's shooting for a gravel to sand ratio of 1.5, then the limits can be modified so that it's always falls within that range. If it does happen that, then we can.
Yes, our intention was not to try to propose new gradations beyond those existing gradation binds, because it's too risky for them to use gradations out of this gradation bind. So our intention was to, because they have a very wide gradation bind, so based on the aggregate shape properties, then we can, so if I have such shape properties, then we can come up with gradation within this bind to achieve the optimum shear strength. So we need to have a method, for example, in that gradation bind, which one will give me optimum gradation? If I have aggregate shape property like this, like uncrusted gravel, crusted stones.
Okay, thanks for your time.
Okay, thank you.
There'll be no presentation next week. No seminar.